Greetings, ladies and gentlemen. Welcome back. In this video, I'm going to discuss the temperature dependence of the rates of chemical reactions. I'm also going to talk about factors that influence and to some extent control that behavior. And finally, I'm going to go over some of the physicochemical techniques that allow us to study the rates of chemical reactions. Well, experiments show that the rates of most chemical reactions increase with temperature. In fact, experimentally, it has been shown that many organic reactions in solution lie somewhere in the range spanned by the following two reactions: the hydrolysis of methyl acetate and the hydrolysis of sucrose. For the chemical reaction of hydrolysis of methyl acetate, the increase in temperature from 25 degrees Celsius to 35 degrees Celsius increases the numerical value for the rate constant by a factor of 1.8, while for the hydrolysis of sucrose reaction, the same increase in temperature, that is from 25 degrees Celsius to 35 degrees Celsius, increases the rate constant by a factor of 4.1. Now, unlike reactions in solutions, reactions in the gas phase typically have rates that are only weakly sensitive to temperature. However, in biochemistry, enzyme-catalyzed reactions show a much more complex temperature dependence. Indeed, raising temperature may invoke conformational changes, which may in turn lower the effectiveness of the enzyme and thus decrease the rate constant. The experimental evidence suggests that almost all reaction rates show a very much similar dependence on the temperature. Indeed, it has been pointed out that a graph of natural log of rate constant plotted as a function of inverse temperature, where temperature has to be in kelvins, should give a straight line that will be characteristic of the reaction. So again, the plot of the natural log of rate constant as a function of inverse temperature, where the temperature is in Kelvin and therefore the inverse temperature is going to be in inverse Kelvin, should give us a straight line. Now the mathematical expression is given by the so-called Arrhenius equation. So in this slide, I'm showing two equivalent forms of the Arrhenius equation: the logarithmic form and that is on the left, and exponential form that is on the right. So the logarithmic form on the left shows that this is the equation of a straight line where the linearized y is the natural log of rate constant and the inverse temperature is x. And then the slope will be equal to the negative of the parameter known as activation energy that has dimensions of energy and is commonly expressed in kilojoules per mole, divided by gas constant, and the y-intercept is going to be equal to the natural log of the so-called pre-exponential, or as recently suggested, frequency factor, which has exactly the same units as the rate constant k. In fact, you can see from the exponential form of the Arrhenius equation that indeed pre-exponential factor or frequency factor a has exactly the same unit as the rate constant kr, because the exponential term, of course, is dimensionless. Now together, the frequency factor or pre-exponential factor A and activation energy E sub A are known as the Arrhenius parameters of the reaction. Now, reactions that have high activation energy means that such a reaction is going to be sensitive to temperature, and the Arrhenius plot for such a reaction will have a fairly steep slope. And it's going to be opposite for reactions that have low activation energy. So the dependence of rate constant for such a reaction is fairly weak, and therefore the slope of the Arrhenius plot is shallow. And of course, when activation energy is zero, it means that the reaction rate is not dependent on the temperature. It is so-called temperature invariant. So again, you can see since the first of all that the slope is the negative of activation energy over R, and you can see that the slope is going to be negative because activation energy is positive and gas constant R is positive as well. And then the magnitude of the slope is going to be governed by the numerical value of activation energy. The greater the activation energy, the steeper the slope. Well, in this slide, we are showing Arrhenius parameters, the pre-exponential or frequency factor A, and the activation energy E sub A for several reactions of different orders. So we have first order reactions and second order reactions in gas phase and in solutions. And what you immediately see is that the activation energy always has the same units. So activation energy has the dimensions of energy, hence the name, and it is commonly expressed in kilojoules per mole. However, the units of pre-exponential or frequency factor A depend on the order of the reaction. So as we noted just a second ago, the exponential form of the Arrhenius equation shows that the unit of pre-exponential factor should match that of the rate constant. Therefore, it will have the unit of inverse second for first order reactions, but liter per mole second for second order reactions. And you can also see that the activation energy are fairly different between 0, for example, which we said in this case, the rate constant will be essentially independent on the temperature, to something like, I don't know, 250, 260, or 270, or even more than 300 kilojoules per mole. Now, once activation energy is known, it is then possible to predict the value of a rate constant K prime at a temperature T prime from its value K at another temperature T. So again, if we know the value of the rate constant K at temperature T, then we should be able to, once we know the activation energy, we should be able to predict the value of rate constant K prime at temperature T prime. So all we need to do is write out the Arrhenius equation for two different temperatures and two different rate constants. So here, the first one here on the left is written for the original rate constant K measured at temperature T. And then the second equation we write for temperature T prime, at which, of course, we expect the rate constant to change to the value K prime. Subtracting one from the other gives us the difference between the between the natural logs of the rate constants, of course, using logarithmic identity that ln of x over y equals ln x minus ln y. Now we can collect or we can combine these two terms into a single term, which gives us the natural log of the ratio of the two rate constants, where the new rate constant K prime at temperature T prime is a numerator and all rate constant K at temperature T is in denominator. And on the right hand side, we have the difference between the activation energy and pre-exponential terms, and assuming that pre-exponential factor does not change with temperature, the right-hand side of this equation is going to only depend on the two temperatures, temperature T and T prime, and then the activation energy, EA. And notice that this expression is very similar in its mathematical form to the so-called Van Hoff expression that shows the dependence of the equilibrium constant on temperature, right? So the only difference is that in the Van Hoff expression we have equilibrium constants, and here we have rate constants. And in place of activation energy that you see in this expression, the Van Hoff expression has the reaction enthalpy. Okay, so here's an example for a reaction with activation energy of 50 kilojoules per mole and an increase in temperature from 25 Celsius, which is conventional room temperature, to 37 degrees Celsius, which is body temperature, corresponds to increase in rate constant by a factor of 2.2. So in this case, uh, the increase in temperature from 25 to 37 Celsius, again 12 degrees Celsius or Kelvin in this case as well, basically slightly more than doubles the rate constant. Now the question, of course, is which factors control the value of the rate constant? In order to answer this question, we need to investigate our Arrhenius equation, and it is convenient to use the exponential form of this equation that shows that rate constant is directly proportional to the pre-exponential factor or frequency factor A, and then depends exponentially on the value of temperature through activation energy. So the two factors that we have to consider are the activation energy and the frequency or pre-exponential factors. So these two empirical parameters determine the temperature dependence of the rate constant. And in order to understand the physical meaning of this Arrhenius parameters, we invoke the so-called reaction dynamics, which studies the history of molecular events that transform reactants into products. And again, reaction dynamics, the goal of reaction dynamics is to provide physically rigorous interpretation of Arrhenius parameters. Again, it should not come to you as a surprise that you can simply determine the Arrhenius parameters empirically, right? So all you need to do is measure or determine, I should say, rate constant for a reaction of interest at least two different temperatures, preferably more. Okay, and of course, then using the Arrhenius equation, you can determine empirically the activation energy and frequency factor or pre-exponential factor. Now the question is, what's the physical meaning of these parameters? And that's where the reaction dynamics, which is a subdivision of kinetics, should tell us. Now the first successful explanation for Arrhenius parameters was provided by the so-called collision theory, which was developed in the first quarter of the 20th century in, you can see 1916, 1918 by Trotz and Lewis. Now they consider, unfortunately, only gas phase bimolecular reactions. So basically you have collision of two molecular species A and B that go on to form product P. And of course, they only considered basically the second order reaction rates. Now, reaction under this condition occurs only if two molecules, which are represented as hard spheres, collide with a certain minimum kinetic energy along their line of approach. So in these two diagrams that you see at the bottom on your left side and right side, you can see how the two reactants, and I'm going to denote them as R, and suppose, again, this is species A and species B, right? So you have a collision between two reactant molecules A and B. On the left-hand side, however, there is insufficiently vigorous collision taking place because after reactant molecules collide, they bounce apart unchanged. So in such scenario, in such case, we can argue that the two species, the two molecules, and again, in this theory, the molecules are represented as hard spheres, they do not have enough kinetic energy along their line of approach to form products. However, on the right-hand side, we have exactly the same two hard spheres of molecular species A and B that do approach each other with sufficient kinetic energy And upon collision, the two molecules go on, the two species, the two molecular species go on to form products P. The progress of a chemical reaction can be traced using the so-called reaction profile. Reaction profile is basically a graph that shows variation in potential energy as two reactant species approach, collide, and then go on to form products. It is usually a two-dimensional plot along the y-axis of which we show the potential energy, and along the horizontal x-axis we plot the progress of reaction, which sometimes can be associated with the so-called reaction coordinate, which could be a distance, could be an angle, or a combination of those. Now, suppose that our reactants have a certain potential energy E P sub R. And as reactant species get closer to each other along their line of approach, the potential energy is of course increases, and we understand why that is. We already mentioned that at intermediate and long range, it is the attractive forces that dominate, and those forces are usually related to the so-called dispersion type interaction. However, as molecules get closer to each other, it is the repulsive forces that start to dominate. And indeed, repulsive forces are much more important at short range separations, or they prevent molecules to collapse into a singularity. So as reactant molecules, reactant species approach each other along the line of approach, the potential energy increases and eventually reaches a maximum, which is then identified with the so-called activation barrier. Activation barrier is basically the energy that is needed to be provided in order for the reactant species to react and then go on to form products. So you can think of this activation energy being energy that can be obtained from a collision, again, sufficiently vigorous collision, so that uh, reactant molecules are able to go over the activation barrier and go on to form products. So again, we can argue that for a successful reaction, reactant molecules must approach with sufficient kinetic energy along their line of approach that would allow them to go over the activation barrier. And again, the physical meaning of this activation barrier is basically it is activation energy of the reaction that we already saw in the Arrhenius equation. Now, collision theory can actually account for the so-called Arrhenius behavior. First, let's introduce the quantity that is known as collision frequency, which is basically nothing else but the rate of collisions between reactant species A and B. Now, it should be obvious to you that collision frequency, that is the rate of collisions between the molecules, should be directly proportional to concentrations of reactant species A and B. For the greater the concentration, the higher the rate of collisions. So therefore, collision frequency will be proportional to the product of concentrations of reactant species A and B. Now, at the same time, collision frequency must be multiplied by a certain factor, let's call this F, that represents the fraction of collisions that occur with sufficient kinetic energy along the line of approach. And again, that kinetic energy along the line of approach has to be equal or greater than the activation energy, for only then the molecules may go over the activation barrier. Indeed, only those collisions that have enough kinetic energy along the line of approach, only those collisions will lead to formation of products. High kinetic energies in other directions does not lead to formation of products. The question, of course, is how to estimate, how to calculate that factor F. Well, in order to do that, we go back to the Maxwell-Boltzmann distribution of speeds. Just to remind you, it's a plot that shows the number of molecules as a function of speed. And we recall that only a small fraction of molecules in the gas phase have very high speeds. However, we also know that kinetic energy increases as square of velocity, right? Or speed, we know that kinetic energy is 1/2 mv squared. So that at high temperature, there will be a larger fraction of molecules that will have high enough kinetic energy because they have sufficient velocity to get them over the activation barrier. So they have enough kinetic energy to bypass, to go over the barrier. Now, the fraction of collisions that occur with sufficient kinetic energy along the line of approach can be determined using the so-called Boltzmann distribution, which is basically nothing else but the exponential function. And in exponent, we have the negative of activation energy divided by the product of gas constant and temperature. Therefore, we can conclude that the rate of reaction will be proportional to the collision frequency, which again we know in turn depends on the concentrations of reactant species A and B, multiplied by the fractions of successful collisions that allow to go over the activation barrier. Comparison with the second order rate law, right, where remember for the second order rate law, says that the rate of chemical reaction is equal to rate constant times the concentration, the product of concentrations of, in this case, reactant species A and B, gives us the expression for rate constant, which is nothing else but the pre-exponential factor or frequency factor, which is equal to collision frequency product of the concentrations of reactant species A and B, and the rate constant is going to be proportional to the Boltzmann factor. Now, we can therefore conclude that collision frequency suggests the following interpretations for the Arrhenius parameters. The Arrhenius parameters A, which again I probably should have mentioned earlier, that in older literature is called the pre-exponential factor, and apparently in the new editions of the Atkins textbook, it is called frequency factor. It's basically a constant of proportionality between concentrations of the reactants and the rate at which the reactant molecules collide. And the activation energy is the minimum kinetic energy required for a collision to result in reaction. It means it is the minimum kinetic energy that allows molecules to go over the activation barrier, and the height of the activation barrier is the activation energy. Now it turns out that for this collision theory, the value of pre-exponential factor or frequency factor A can be calculated directly from the kinetic theory of gases. Remember, in kinetic theory of gases, we represent molecules as hard spheres of a certain radii. So here we have our frequency factor A, which is equal to the collision cross-section, that is target area presented by one molecule to another, times the square root of the term that depends on temperature and the so-called reduced mass of the two colliding molecules A and B, where the reduced mass is equal to the product of the masses of the two colliding species A and B divided by the sum of the same masses. And of course, since we're talking about molar quantities, we need to multiply the whole thing by Avogadro's number. Now, make a note that in this formula, which is numbered at 10.21 in the 5th edition of the textbook, it is squared in the 5th edition, and it should not be squared. but it is of course been fixed in the 6th edition and I believe in the 7th edition as well. Now, if our molecules are represented by hard spheres, and suppose the radii of those spheres are Ra and Rb, then the collision cross-section will be pi times r squared, where r squared is the sum of the radii of reactant species A and B. Okay. Now, application of collision theory for some of the reaction, especially in the old days, showed that it to be very promising. For example, in this slide, I'm showing the so-called old calculation for pre-exponential of frequency factor A for decomposition reaction of hydrogen iodide into hydrogen, diatomic hydrogen and diatomic iodine at room temperature, and there is a strikingly similar agreement between what's predicted from collision theory, again using hard sphere approximation for molecules, and the experimentally determined pre-exponential factor from, of course, the Arrhenius plots. Now, unfortunately, in this particular example, even though it looks good, the agreement is accidentally fortunate. This simply happens because the errors that are introduced in the calculation of predicted value of pre-exponential factor simply cancel out. It turns out that for many reactions, there are large discrepancies between observations and predictions. And for complex molecules, the observed frequency factors or pre-exponential factors are lower by several orders of magnitude than those calculated by the collision theory. And deviations from theory are also encountered with solution reactions involving ions and dipolar substances as reactants. Now, of course, I think it makes perfect sense to attribute the sources of discrepancies in the use of the hard sphere kinetic theory of gases when evaluating frequency of collisions. Of course, we know that most molecules are not spherical, right? And hard sphere approximation is simply too crude for the accurate and precise predictions. Now, to uh, bypass this issue, or at least fix that issue to some extent, uh, scientists came up with the idea of so-called steric factor. The idea here is actually fairly simple. The molecules should not only collide with sufficient kinetic energy along their line of approach, but also must come together in a specific relative orientation. Okay. Consider the following example. Suppose we have a diatomic molecule. Again, let's call it HCl. Again, I just made up these chemical elements. It's supposed to combine with sodium atom to form sodium chloride and hydrogen. Again, we're talking about some completely fake identities of atoms. I mean, or you can say, okay, a diatomic molecule that is made from green sphere and purple sphere supposed to um, um, collide with a molecule represented by a red sphere in such a way that the green sphere is then detached from the purple sphere and attached to the red sphere. Okay. Now, in the first example, we can see that the two molecules, even though they may be colliding with sufficient kinetic energy along their line of approach, the orientation is such that it will be impossible for the two molecules to exchange the green sphere, simply because the point of collision is actually a purple sphere, right? Now, however, if we change the orientation at which the reactant species, red sphere and the diatomic molecule represented by green and purple sphere, if they collide in such a way that the red and green spheres collide, so the orientation is different, the relative orientation of diatomic molecule is different for these two scenarios, then actually such reaction is going to be successful, and the bond between the purple and green spheres will be broken, and the new bond between the green and red spheres will be formed. So in this case, the reaction rate will be proportional to the probability that encounter occurs in the correct orientation. So again, not only the molecules need to have enough kinetic energy or should collide with sufficient energy along the line of approach, but also one has to introduce the idea of orientation, because again, molecules are not spherical. Most molecules are not spherical, of course. So therefore, the frequency factor or the pre-exponential factor should also include, think of it as a fudge factor that is called steric factor P, and our collision cross section is multiplied by that steric factor that gives us the so-called effective collisional cross section sigma star. So again, multiplication of collisional cross section in the formula for the pre-exponential factor. We're going to replace that collision cross section with the effective collisional cross section, in which we take the collision cross section calculated from kinetic molecular sphere, kinetic molecular theory, and then multiplied by steric factor. The steric factor varies, so basically it has to be a positive, obviously, or I should say non-negative value. So the value of 0 for steric factor means that no relative orientations lead to reaction. So no matter how the species collide, the reaction will not take place. Steric factor 1 means that all relative orientations will lead to reaction. And it is even possible for the steric factor to be greater than 1, which means that molecular orientations effectively extend the collision cross-section far beyond the value expected from simple mechanical contact as predicted by kinetic molecular theory. Let's consider a couple of examples. So we have, again, so-called bimolecular reactions where you have two nitrosyl chloride molecules colliding, forming or going on to form products, the two nitrogen oxides and diatomic chlorine. And in this case, we can see that the steric factor was estimated to about 0.16. Well, what does it tell you? Well, it tells you that there is certainly some orientational dependence present in the reaction, but it's not severe. Certainly not as severe as in the case of this other bimolecular reaction, in which hydrogen is colliding, is combining with ethene, producing ethane. And in this case, you can see that the steric factor is many orders of magnitude smaller than the one shown for the nitrosyl chloride reaction, which means that the second reaction has very stringent orientational requirements. So molecules must collide at very specific orientations, and even small deviations from these orientations will render the collisions unsuccessful, which means such collisions will not go on to give us products. There is another example, a classic example, where the two molecules, or in fact it's an atom and a molecule, so potassium atom and diatomic bromine molecule collide, where one of the bromine atoms actually leaves the diatomic species and goes on to combine with potassium. Now for this particular reaction, the steric factor was found to be several times greater than 1, right? So it means that um, the distance of approach for successful collision is much greater than the distance for deflection for non-reactive collision, which means there are many more successful collisions found in this reaction, determined to be in this reaction, determined to take place in this reaction, that what's predicted by collision theory and kinetic molecular theory. Now, in this case, the mechanism is likely due to the so-called harpoon mechanism, as the two reactant species, potassium and diatomic bromine, approach each other. The electron, which acts as harpoon, flips to, and that's electron, of course, remember the s electron on the outer shell from potassium, which we know is barely tied up to the nucleus. So the ionization energy of potassium is actually, the first ionization energy, of course, of potassium is very small. So that outer s electron, which is not very tightly bonded to potassium due to shielding by all the inner electrons, it flips to diatomic bromine molecule, and then strong Coulomb type attraction will take place between the two new ions, and that allows one of the bromine atoms to get detached. So the bond between the two bromine atoms gets broken, and that bromine atom leaves the diatomic species and gets attached to potassium. So in this particular case, we can argue that harpoon mechanism significantly extends the collision cross-section that is predicted via, a um, simple kinetic molecular theory. Now, the problem with collision theory, that first of all, it takes into account only bimolecular reactions. Again, you have two species colliding, combining. And even more severe deficiency, it does not take into account solvent effects, because you cannot simply incorporate easily solvent in collision theory. So a new, much more sophisticated, but much more universal, if you would, much more widely applicable theory has since been developed, and that theory is known as transition state theory or activated complex theory. So the idea is similar. We're trying to trace the molecular events as a function of progress of reaction in terms of potential energy. As two reactants approach, their potential energy rises and reaches maximum. Again, in a very similar manner that we just saw for uh, collision theory. So again, we are looking at how the potential energy changes as a function of progress of the reaction, and the progress of the reaction is monitored through a reaction coordinate. Again, it may be the distance between the atom one of one reactant species and atom two of another reactant species. It may be angle, maybe a combination. And as reactants get reactant molecules, reactant species get closer to each other, the so-called activated complex is being formed. An activated complex is basically a cluster of atoms that is poised to pass on to products or to collapse back into the reactants from which it was formed. So basically, it also depends on the amount of energy that is accumulated in activated complex. For it basically is given two choices. It can either, once it is formed, it can fall back. So basically, fall back into reactants, or it can go over the activation barrier and go on to form products. So let's think about what this activated complex may look like. Well, in an activated complex, only some of atoms, those are at the actual reaction site, are significantly loosened and a little bit rearranged. The bonding of the other atoms remains almost unchanged, and I'll show you example in just a second. Now, the beauty is that the concept of an activated complex is applicable to reactions in solutions as well as to the gas phases, because activated complex may not only include the atoms of the reactant species, but some of the solvent molecules. Now, keep in mind, however, that activated complex is not a reaction intermediate. It exists for only a few picoseconds and cannot in general be isolated and studied using conventional methods. And by the way, that's where theoretical calculations come in very, very handy. Now, an example of an activated complex that we can consider comes from so-called femtochemistry. So basically, it is the studies of species with very short lifetimes using femtosecond, femto, remember, 10 to the power of minus 5 seconds, pulse lasers, uh, was pioneered by, I think, Egyptian-American scientist Ahmed Zewail, who was Zewail, I think, who actually received Nobel Prize for it. Now, this is a typical um, uh, double pulse technique, where pump probe technique, where the first of the laser pulse leads to the dissociation of a complex, while the uh, second pulse that follows is basically a probe. So, you're using some sort of spectrophotometric method to determine what is actually happening after that first pulse that initiates some chemical reaction. So the frequency of pulse is going to be equal to the frequency absorption of the free fragmentation products. And in this case, absorption basically is the measure of absorbance of the dissociated products. The classic example is dissociation of iodine cyanide. So suppose we have here cyano group, and the idea here is that the first laser pulse will break the bond between the iodine and the cyano group, and the second pulse, the probe pulse, will be monitoring the absorption of free cyano group. And it turns out that the signal from cyano group, again free, unbonded, cyano group, remains zero until the fragment or iodine goes in one direction, the cyano group, say, goes in another direction. Those fragments will have separated by about 6 angstroms. Just to give you an idea, maybe the length of a triple carbon nitrogen bond is maybe something on the order of, I don't know, 1, maybe 1.2, probably 1.2 angstroms or so. So again, we're talking here significantly smaller distance than 6 angstroms. So again, I do not exactly remember the bond distance, the triple bond distance between carbon and nitrogen. Now, single carbon-carbon bond, for example, is 1.4 angstroms. Okay. All right. And so the time it takes for the two fragments to separate at about 6 angstroms. Again, the iodine is moving from cyano group, separate from cyano group, and the time that it takes for that separation to take place is about 200 femtoseconds, which is again very, very impressive. And of course, since then there have been a lot of femtosecond studies performed, and I think with years, each year the number increases. They've been, this kind of technique has been used to study Diels-Alder reaction, nucleophilic substitution, cleavage reactions, etc. And apparently also these kind of studies are important when learning about energy converting processes of photosynthesis and light induced processes of vision, because again those processes take place on a very short femtosecond time scale. Now let's consider a general progress of a binuclear reaction to sort of have a little bit of connection to our collisions theory. So again, we are considering reactant species A and B that come in contact, distort, and begin to exchange or discard atoms. So again, our original reactants have certain potential energy EP sub R. In this case, we're basically following the same kind of progress as predicted or as discussed in the collision theory. As the atoms the reactant species get closer to each other, the potential energy increases, and this is because the reactant species, they come in contact, distort, and begin to exchange or discard atoms. Now, again, in this case, the energy that allows the energy that allows to overcome the restrictions due to potential energy coming from kinetic energy of collision motion. Now, when the molecules have already undergone significant changes in terms of their geometries, again, it could be local, again, could be localized to only, a small part of each species, an activated complex is being formed and potential energy rises to a maximum. So activated complex in terms of energy occupies the area around the maximum of this activation barrier peak. And as at the very top of that peak, right, where the activation energy is maximum, right? So remember, the difference between the reactants and the maximum of this peak is nothing else but activation energy. That is the location that corresponds to the so-called transition state. So again, a certain reaction coordinate that corresponds to the maximum in potential energy gives us the so-called transition state. And you can think of transition state of the reaction as this crucial atomic configuration at the maximum of potential energy. And small further distortion will send the atomic configuration in the direction of products, but somehow perhaps another vibration or a vibration in a different opposite direction will distort the transition state and make it fall back towards reactants. Now, the reaction coordinate that we've already mentioned several times is basically an indication of the stage reached in this process. So again, for very simple, I don't know, like isomerization reactions, a reaction coordinate can be, again, distance between atoms, can be angle, maybe torsion angle or so-called dihedral angle. But the idea here is on the left, we have undistorted, widely separated reactants. So again, as long as they stay far apart from each other, the total potential energy does not change. On the right, we have the same situation, but for products. Again, as long as our product species are separated by significant distance, their potential energy is unchanged. And in the middle, we have already the increase in potential energy that leads eventually to the formation of the activated complex. And the goal of transition state theory is to find an expression for the rate constant by tracking the history of the activated complex from its formation by encounters between reactants. So again, that's where it starts to form, and until it uh, decays into products. Okay, so again, the idea here is to study the events that lead to the formation of activated complex, that the changes that the geometrical changes that the activated complex undergoes, and that eventually allow it to fall to produce products. Now in this diagram, I'm actually showing a slide from a PhD dissertation of my wife, who defended her PhD in physical chemistry, physical theoretical chemistry from University at Buffalo quite a few years ago. So they were studying theoretically the ruthenium nitrosyl compound. So you have ruthenium metal in, as you can see, octahedral coordination. You got 5 amino groups and nitro group, again, ruthenium nitrosyl complex. So in the ground state, which is the most stable, energetically favorable energy state, the nitro group is bonded, is bonded to ruthenium from the using the nitrogen atom. And in this particular complex, we know its geometry well from experiment, from X-ray diffraction studies, where you can just crystallize this compound, put it on an X-ray, single crystal X-ray diffractometer, and determine all the geometrical properties of this molecule, including, for example, NO bond distance between ruthenium and nitrogen, and distances between the uh, between the ruthenium and nitrogen atoms, as well as ruthenium nitrogen oxygen angle. So it's this angle. Oops, sorry, this angle right here. Now the same. Now, unfortunately, again, experimentally, they were only able to look at the ground state and also at these metastable states. Okay. Now, what's a metastable state? Well, this is the state that has high energy, that the ground state, the most energetically favorable state, but that metastable state can be frozen in time by cooling the system to a low temperature. So the idea is to radiate your molecule that is originally in ground state with a laser pulse while the molecule is being cooled at a very low temperature. I forgot what the actual temperature is. And the molecule will go onto one of these metastable states. They were called metastable state 2 and metastable state 1. Okay? And the molecules will stay in those states until the temperature is increased. So, and only then those two metastable states will decay back. They will go back to the original ground state. So again, at normal temperature, room temperature and low temperature, under just ambient conditions, it is the ground state that will dominate. However, the reaction in solid state, so you take the crystal of your molecules in ground state, you hit them with a laser, and again, I don't remember exactly the frequency or the wavelength of the laser that they used. So, well, while the system is cooled, the system will go either into metastable state 2 and metastable state 1. What's the difference between those metastable states and the ground state? Well, you can see in metastable state 2, the nitro group is actually bonded sideways. Okay, so this is kind of some sort of, I don't know, um, pi-type interactions between the nitro group and ruthenium. So obviously, of course, all these bonds involve d orbitals. And then in metastable state 1, the bonding of the nitro group to ruthenium is through oxygen, not through nitrogen. And again, the X-ray structures for not only ground state, but also for the two metastable states were obtained using X-ray diffraction. However, what happens in between was not possible to study experimentally, and it was decided to perform theoretical calculations. So these numerical values outlined in blue are the results of theoretical calculations using the so-called density functional theory. And you can see that unlike experiment, the theory is also able to provide the energies. So the energies here are in electron volts. Just a reminder that the energy of 1 electron volt is the amount of energy that 1 electron acquires as it accelerates through potential of 1 volt. And you can see that there's a very good agreement between the geometrical parameters that were determined theoretically as compared to experimental values. But then once they were satisfied with the level of theory that they chosen to describe this compound, they were able to predict and investigate the geometries in the two metastable states. So this is 1 and then 2, and also plot reaction profile. In this case, notice that this is a potential energy, right? Just like we saw a second ago. So reaction profile is a two-dimensional graph of potential energy. In this case, it is expressed in electron volts. Again, electron volt is the amount of energy acquired by 1 electron as it accelerates through potential of 1 volt as a function of reaction coordinate. And in this case, reaction coordinate is the angle ruthenium, nitrogen, oxygen. So again, it is this angle right here, ruthenium, nitrogen, oxygen. Again, it is at 180 degrees, right? Essentially, straight line in ground state, but it changes to 83 degrees in metastable state 2. So ruthenium, nitrogen, oxygen. So this angle right here is 82 degrees, not exactly, obviously 90. And then it goes back to 180 degrees, but now it is through oxygen. And again, what is really interesting here is that they were able to plot to determine the reaction profile for this reaction. And again, just a reminder, this is the location, this is the energy of ground state. This is the energy, of metastable state 2. This is the energy of metastable state 1. And this is here, this is where the activated complexes are formed. So in this region number 1, we have activated complex that is formed between as your ground state is converted into metastable state 2. And in this region number 2, you have activated complex that is formed as your metastable state 2 goes into metastable state 1. And at the top of these reaction profiles here, you have the activation energy. So this is the activation energy, let's call it E sub A1, which is needed for the ground state to go into metastable state 2. And then, and maybe I can use another color here. And of course, these results were published in scientific journals. Okay, so then E sub A2 is the activation energy that allows metastable state 2 to go into metastable state 1. And again, at the top of these peaks, you have so the top of these peaks here, you have transition state, let's call it 1, and then here transition state 2. Okay, so transition state 1 is between ground state and metastable state 2. and transition state 2 between metastable state 2 and metastable state 1. Why am I discussing this in such a deal there? Well, because in this case, you're looking at the actual chemical system that was studied, and the results were rigorous and have been published. Okay, so let's take a look what is happening to this graph. So let me see if I can, oops. Oh, there we go. So, and again, you can see how the molecule distorts. For some reason it won't let me. There we go. Again, unfortunately, I don't think I can stop it. Again, you can see how the angle, ruthenium nitrogen oxygen angle, is changed. So again, look what's happening here in this region. Right? So again, of course, the rest of the molecule does respond, right? But not very significantly. Okay. So again, in this case, you can argue that the activated complex is essentially localized to ruthenium and nitro group, but the rest of the molecule it does respond um, to the changes in the activated complex. Okay, introduced in the activated complex, taking place in the activated complex. All right, enough about this. All right, so let's denote our activated complex as C, and activated complex is formed from the reactants A and B, as we just saw a second ago. And suppose there is an equilibrium between the concentration of reactant species A and B and activated complex C. So we have chemical reaction and we have equilibrium, so we can immediately write out the expression for equilibrium constant. Now keep in mind, of course, that technically these are all concentrations divided by standard concentration of 1 mole per liter. Okay, now this will probably cancel and that will go up to the numerator. So at the transition state, motion along the reaction coordinate, just like you saw, corresponds to some complicated collective vibration-like motion of all the atoms in the complex. Again, in a previous example, you saw the activated complex was fairly simple, but it did, so the formation of activated complex did introduce some changes in the geometry of the rest of the molecule and the motion of solvent molecules, if any, are involved. In this case that you just saw a second ago, it was a solid state reaction where the changes were introduced in crystal. And we want to point out that not every motion along the reaction coordinate will take the process through the transition state to the product P. So taking into account equilibrium between reactant species A and B and activated complex C and the rate of successive passage of C through the transition state, remember that the maximum of the maximum of the activation barrier, right? So that gives us the so-called Eyring equation for the rate constant Kr. So Kr here is, and this is kind of interesting, we got like 4 different Ks in this reaction. So Kr here is rate constant. Then we have kappa here, so that's Greek letter kappa. It is known as transmission coefficient. I'm going to discuss its physical meaning in just a second. This little k here is, actually it says right here, it's Boltzmann constant. And the k here is equilibrium constant. Equilibrium constant. What equilibrium constant? Well, it's equilibrium constant for the equilibrium between the reactants and the activated complex. Okay? And H here is Planck's constant. So The physical meaning of transmission coefficient is actually fairly straightforward, though it's not usually easy to determine its numerical value. It basically accounts for the fact that the activated complex does not always pass through the transition state, and in the absence of additional information, we have no choice but to set it to 1. So basically, we're saying that, well, um, we have 100% of transitions through the transition state to form products. Now let's analyze this equation a little bit more. The term here, kt over h, it actually has dimensions of frequency, and it arises from consideration of motions of atoms that lead to decay of activated complex into products as bonds are broken and formed. And remember, we can multiply that by transmission coefficient kappa if not all such motions are successful in forming products. Now, increase in temperature, and notice temperature is in numerator, enhances the rate by causing more vigorous motion in the activated complex, which facilitates the rearrangement of atoms and leads to the formation of new bonds. So it is expected for the increase in temperature to increase the magnitude of the rate constant. Now, the problem with the searing equation, that calculation of equilibrium constant here, again, that's equilibrium constant between the reactant species and activated complex. It's very difficult except for simple cases. If we consider a reaction between two structureless atoms, an activated complex being a diatomic molecule with a bond length R, then basically we get same expression for rate constant as that we got for collision frequency if collision cross-section is pi r squared. So here we actually have some agreement between, transition state theory and collision theory. However, it is more useful to express Eyring equation in terms of thermodynamic quantities, okay? Because those are easier to determine than individual molecular events. And the idea is to discuss reactions in terms of their empirical values that we can get. Now recall that equilibrium constant may be expressed in terms of the standard reaction Gibbs energy. We know that. Now, of course, in this context, right, our equilibrium constant for the equilibrium between reactants and activated complex can be called the activation Gibbs energy. So again, we rewrite this expression, right, for the equilibrium constant again between for the equilibrium between reactants and activated complex, and the corresponding Gibbs energy or change in Gibbs energy is known as activation Gibbs energy. Okay. Now we solve this equation. We solve this equation for equilibrium constant and have its expression in terms of our activation Gibbs energy. And now we put into the Eyring equation, and then we expand the activation Gibbs energy in terms of activation enthalpy and activation entropy, and assume that transmission coefficient is 1. So after this manipulation, we have expression for our rate constant in terms of the same quantities that we saw before, such as temperature and the fundamental constants such as Boltzmann constant and Planck's constant. But now we have also the activation entropy and activation enthalpy. And then if we compare the resulting expression here for the rate constant from the Eyring equation with that with the Arrhenius equation, what we see is that the exponential factor, or this frequency factor, is somehow related to the activation entropy, right? And the exponential factor that includes activation energy is associated or is very much similar in form to that that includes the activation enthalpy. So we can basically relate the activation energy with the enthalpy of activation. How cool is that? And we can associate the um, frequency factor A or pre-exponential factor A with the entropy of activation, even though that dependence, as you can see, relatively complicated. So it's an exponential form. Now, transition state theory has many advantages over collision theory. Remember, collision theory only considers bimolecular events, two molecules colliding in gas phase, cannot take into account solvent effects. However, transition state theory can can deal with reactions in solutions as well as in gas phase. It shows that even a complex series of events, not only collisions in gas phase, right, display Arrhenius-like behavior, and it also provides foundation for activation energy, gives some clue to the calculation of steric factor P for the orientation requirements are carried in the activation entropy. For example, if there are strict orientation requirements, enzyme substrate, then activation entropy will be strongly negative because decrease in disorder takes place when activated complex forms, and therefore we expect the frequency factor per exponential factor to be small. Now, in practice, it is sometimes possible to estimate the sign and magnitude of activation entropy and hence to estimate the rate constant. All right, and then the final, I think about 10, 11 slides are on the um, physicochemical techniques that are used to study rates of chemical reactions. We start by looking at spectrophotometry. Basically, spectrophotometry is a technique that measures the absorption of light by a material, and it forms basis for a number of techniques used in chemical and biochemical investigations and allows to study fast reactions, certainly taking place below uh, the second time scale. So the idea is very simple. We have a light source. That light source goes through a prism, right? And then we separate our light into light of different frequencies. Uh, that light is passed through the narrow slit and descend onto the sample, uh, kept in some sort of cuvette, and then the signal is registered on detector as a function of different wavelength. Now notice this prism can be rotated, that we have a wavelength or a beam of a certain wavelength passing through the slit. However, these days we use CCD detectors, charge coupled devices detectors, similar to the ones you have in your photo cameras that allow that has a lot of photodiodes that are sensitive to wavelength of many different frequencies. For example, in our physical chemistry lab, we have our UV vis spectrophotometer that allows that has a CCD detector, two-dimensional detector that has photodiode sensitive to uh, waves, to beams, electromagnetic radiation in both the visible and ultraviolet regions of electromagnetic spectrum. So we don't really need to analyze one wavelength at a time. Instead, we are analyzing all wavelengths at once, which of course is a huge help and saves a lot of time. So the spectrophotometric methods are all essentially based on some form of Beer-Lambert law or the Beer's law. The idea is that the intensity of absorption of radiation at a particular wavelength, so absorption is a function of wavelength, is related to concentration of the absorbing species. One of the forms of Beer-Lambert law is the absorbance is directly proportional to the concentration of species J the length path that the beam travels through the sample, and the constant of proportionality is the so-called molar absorption coefficient. So again, absorbance here, which is also known as optical density in all the literature, again, is directly proportional to the concentration of absorbing species, the path length of the beam in the sample, and the constant proportionality of the molar absorption coefficient. Now, the absorbance or optical density can be defined in terms of the negative base 10 log of the ratio of the incident, the negative base 10 log of the ratio of the transmitted beam and the incident beam. So this is transmitted beam, this is incident beam. Again, a reminder that the expectation is that the intensity of transmitted beam is smaller than that of incident beam. That means the ratio here is less than 1. A log of ratio of something less than 1 is negative. Negative times negative is positive. Okay. Now, of course, using the logarithmic identity, log of x to the power of a is a log to the power of x. So if we have log x to the power of minus 1, of course, which is log 1 over x, it gives us minus log over x. So then we can flip the numerator and denominator, and then we cancel the negative sign here. So absorbance can be written as the positive base 10 log of the ratio of the incident beam and transmitted beam. Now, in fact, the ratio of the transmitted beam and incident beam is also known as transmittance, T, and absorbance can be defined as the negative base 10 log of transmittance or positive base 10 log of inverse transmittance. So here in this diagram, we kind of show the setup. So you have the incident light, right, created by your spectrophotometer. Here's a cuvette with a certain path length here. You have the concentration of species C, which is basically your molarity, and then alpha here actually denotes the molar absorption coefficient. I took this picture from Wikipedia because I like it very much, but unfortunately they're using slightly different notation for the molar absorption coefficient and concentration. So here you can say that, okay, forget this. This is now concentration of absorbing species, and also you have molar absorption coefficient. Now, keep in mind that absorbance is a function of wavelength, while but that's because the molar absorption coefficient is also a function of wavelength. Okay, so again, because molar absorption coefficient depends on the wavelength, you basically have different absorbing ability of species to absorb light depending on the wavelength. Because the molar absorption coefficient depends on the wavelength, the absorbance will depend as well. Now let's talk a little bit more about the molar absorption coefficient. In the older literature, it is called molar extinction coefficient, sometimes just extinction coefficient, or molar absorptivity. As we already mentioned, it depends on the wavelength of the incident radiation. Again, in the good old days, they analyzed by one wavelength at a time. These days, we can analyze many different wavelengths at once due to those charge-coupled devices, which have many different photodiodes that are sensitive to many different wavelengths. It is greatest where the absorption is most intense. The unit is inverse concentration times length. So if our concentration is in mole per liter and the path length is in centimeters, that's what we have, for example, in our spectrophotometers, then it is convenient to express the molar absorption coefficient as inverse concentration, which is, used to be mole per liter, becomes liter per mole, and divided by inverse length. And that is because, notice, the absorbance is dimensionless. So again, if length here in centimeters, concentration is mole per liter, then naturally the molar absorption coefficient should have a unit that will cancel the concentration and cancel the path length. Okay. So again, absorbance does not have any units, and you can see that, and I probably forgot to mention it in the previous slide, but you can see it has no units because it is defined as the uh, log of something, right? Now, Beer's law or Beer-Lambert law is used to determine the concentration of species of known molar coefficients. So if you know, you measure the absorbance, you know the path length for your spectrophotometer, for your cuvette, and if you know the molar absorption coefficient at a given wavelength, you can determine the concentration of species. And of course, this law also allows us to observe appearance or depletion of species during a reaction by monitoring changes in absorbance of a mixture. Now, it is common to make measurements of absorbances at at least two wavelengths, to find individual concentrations of two components, A and B, in your reaction mixture. Now, again, uh, this is where we kind of running out of symbols for our notation. So keep an eye on the on the uh, uh, on the font. So the italicized uppercase A stands for absorbance, while upright A stands for species A. Okay, so the total absorbance of our mixture will be absorbance of species A plus species B, and then we can expand each one of those absorbances as the product of molar absorption coefficient, the concentration, and the path length. Of course, the path length is the same because the reaction mixture is in the same cuvette, right? So we can a little bit simplify that. We can write out absorbance as a function of the sum of molar absorption coefficient and um, concentration for each of the species times the path length. And then you perform this for the two different wavelengths. And remember, the absorbance depends on the wavelength because molar absorption coefficient depends on the wavelength. So now we have two equations for two unknowns, right? Well, we know L, right? We know the molar absorption coefficients, right? We measure absorbances, so it allows us to determine the concentrations of species A and B. So solving these two equations for two unknowns, which are our concentrations A and B, we can determine the concentration of each of the species in a reaction mixture. And think about this, if you perform these measurements at different stages of reaction, you can trace the concentration of those species as a function of product of the reaction. Now, a very interesting situation happens when the molar absorption coefficients of the two species, A and B, are the same at certain wavelengths. So such wavelength is called isosbestic. So it's called isosbestic wavelength, okay? And for isosbestic wavelength, our expression can, the expression for absorbance can be even further simplified because the molar absorption coefficient at that particular wavelength of species A and B are the same. And then what we're looking for is the absorbance is equal to the molar absorption coefficient, right? Which again is the same for species A and B, times the path length times the sum of concentrations of A and B. However, because at any point of the reaction, the sum of concentrations of A and B is constant, it means that the absorbance at that particular isosbestic wavelength is constant as well, even though the individual concentrations of species A and B can change. So suppose again we have our chemical reaction that in which the species A are transformed to species B, some sort of maybe isomerization reaction. Think about, I don't know, the boat configuration of hexane is isomerized to the chair configuration of hexane, something like that. Well, in this case, the absorbance will not change no matter what the stage of chemical reaction is. Okay, so at different stages of chemical reaction where A is transformed into B, the absorbances everywhere else will be different, okay, because the concentrations change and the molar absorption coefficients depend on the wavelength. But for that particular isosbestic point, which is a point that is invariant in the absorption spectrum, the total absorbance will stay the same. Now, it is very unlikely that 3 or more species will have the same molar absorption coefficient at a given wavelength, so observation of an isosbestic point, or at least not more than one such point, is an evidence that a solution consists of only two solutes in equilibrium with each other with no intermediates. And remember, in your experiment 9, where you determine pKa of indicator, you actually do see isosbestic points, okay, several of them, because you only have two species present in your solution, the base form of indicator and acid form of indicator, right? And you're basically converting, say acid form to base form, right? The say concentration of base form increases as concentration of acid form decreases, but the sum of the two concentrations stays the same because you don't change the concentration of indicator, total concentration in your solution. And since at those isosbestic points, the molar absorption coefficients of acid and base form are the same, the total absorbance does not change with those concentrations. All right, and then the final topic that I want to talk about are the experimental techniques. So it's not surprise that special instruments are needed to study fast reactions taking place on the time scale below tens of seconds. The most powerful technique is real-time analysis, where composition of a system analyzed while reaction is in progress. And that composition is usually determined by direct spectrophotometric observations of reaction mixture. The first sort of well-established method dates back to the end of 19th century. It's known as flow method. The idea is very simple. Reactants are mixed as they flow together in a chamber. So you have two syringes, driving syringes. Syringe A squirts, pushes reactant A into the mixing chamber. Syringe B pushes the reactant B into the mixing chamber. Reactants, as they're squirted into the mixing chamber, it's done so at a steady rate, and solutions or solution is thoroughly mixed in the process in the mixing chamber. Okay, and then the idea is that the resulting solution. So this is where again the two solutions mix, and that's when the reaction starts. And then those solutions are allowed to flow through a capillary outlet tube at a speed of about 10 meters per second. And different points of the tube will correspond to different times after the start of reaction. And then this outlet capillary tube is equipped with a movable spectrophotometer. So that spectrophotometer is allowed to move back and forth along this capillary tube. So, and then depending on the location of that spectrophotometer along this tube, basically you can perform the spectrophotometric analysis of your reaction mixture at different times after the start of the reaction. So originally this device was developed, or this technique was developed to study the rate at which oxygen combines with hemoglobin. The disadvantage, of course, is obvious because large volume of reactant solution is necessary because mixture must continuously flow through the apparatus. So again, you move your spectrometer back and forth, or at least one direction, following the progress of the reaction. Now, what is also especially important for a very fast reaction is that flow must be rapid if it is to spread the reaction over an appreciable length of the tube. The stop flow technique is basically a modification of the flow method that allows to study faster reactions. We're talking on the millisecond time scale. The initial step is very similar to that of flow method. Two solutions are mixed very rapidly in less than 1 millisecond by injecting them into a mixing chamber. So again, we have two driving syringes. One is going to inject reactant A, the other is going to inject reactant B into the mixing chamber. The flow is turbulent in order to achieve complete mixing very quickly. And behind mixing chamber, there is an observation cell, again fitted with spectrometer, but that cell also has a plunger that moves back as liquid floods in. Plunger comes against a stop after a certain volume of liquid has been admitted. And basically filling observation chamber produces the initial sample of reaction mixture. And time dependence of the reaction is monitored spectrophotometrically like we've done before. And the advantage over the flow method is small amount of sample can be used in this technique. The flash photolysis method, and you can see this is already middle of the 20th century, allows studying even faster reaction. It primarily applies to study of reactions that can be triggered by light. Again, just like the femtochemistry technique, it's a palm probe technique. Sample is exposed to a strong short pulse of light, which is a palm pulse from a laser or a flash lamp, and depending, of course, on the device that produces that first pulse, the pulse may have a duration of nanoseconds, picoseconds, or femtoseconds. Now, this first strong pulse starts chemical reaction, and then the subsequent pulse will probe the sample, usually spectrophotometrically. Okay, so absorption of light by the sample is recorded within a short time interval. Test pulses, those probe pulses, in order to monitor reaction processes initiated by the original pump pulse. So as we already mentioned, femtochemistry is a study of species with very short lifetimes on the order of femtoseconds using femtosecond pulsed lasers. Apparently, I think they're even moving to attosecond pulses, but again, don't quote me on that. So again, first pulse results or produces the chemical reaction, suppose dissociation of a complex. Second pulse is a probe that gives you the spectroscopic picture of the event. The frequency of pulse will be equal to the frequency absorption of the free fragmentation products, and absorption will be equal to the measure of, or will give you the abundance of dissociation products. And we already looked at the dissociation of iodine cyanide. The idea here is that your probing pulses will be monitoring the absorption of free cyano group. So as the experiment showed, signal from free cyano group remains zero until fragments separated by about 6 angstroms, which takes about 205 femtoseconds, which again is fairly impressive. And there are examples, other examples of femtochemical studies that have been done in the recent years. So this is what this kind of field is relatively young. We're talking about, well, maybe 20, 30 years at most. But it is very active. Relaxation technique, again, dates back to mid 20th century. It's also called perturbation relaxation. And the idea is fairly simple. First, you establish equilibrium in a reaction mixture that gives you the initial state, and that this equilibrium is disturbed by a rapid change in conditions such as pressure, temperature, perhaps pH. And then relaxation is monitored, where relaxation is defined as return to equilibrium at new conditions from its initial state. Now, again, we're using spectroscopic techniques to monitor the process, and temperature perturbation or T-jump experiments are the most common of these, and we're going to talk about that in chapter 11. And then I think the last set of methods that I would like to mention are quenching methods. Basically, the idea is to stop or quench the reaction after it has been allowed to proceed for a certain period of time, and then composition is analyzed at leisure. And then we distinguish between chemical quench flow methods, where once reactants are mixed, as we have them in the flow method, the reaction is quenched by another reagent. So you basically stop the reaction at the desired time interval. And the advantage here is that spectroscopic fingerprints are not needed to measure concentrations of reactants and products. And then the other type of fairly popular type of quenching methods is freeze quench method, where a reaction is quenched by cooling the mixture at a very high rate within milliseconds. And then, of course, concentrations of reactants, products, and perhaps even intermediates can be identified and measured spectroscopically. Okay, well, this is the end of chapter 10. So notice all of a sudden we are almost halfway through kinetics. Now in the next series of lectures, I'm gonna cover chapter 11, and we will be done. So in the meantime, as always, you guys be good, be safe, study hard, and I will see you in my next video. In the meantime, you all have a great day now. Bye bye.